How's it going, ladies and gentlemen? Mr. Donahue here again. This time we're going to take a look at some practice problems for rates of decay. So number one, what is the rate constant for a radionuclide with a half-life of 2.3 times 10 to the 5th years? So the first order kinetics equation is going to be the equation we use for radioactive decay, because radioactive decay follows first order kinetics. All right, now if we go at one half-life, we can solve for the rate constant in terms of the half-life. So you just kind of plug in at some time, you're going to have 50% at one half-life. T is going to be your half-life, and A0 will be 100%. So when we do a little algebra and we rearrange to solve for K, we get K equals 0.693 over T 1/2. So now we could just plug in our numbers. 0.693 divided by 2.3 times 10, times 10 to the 5th years. And when you plug and chug that, you end up with 3.0 times 10 to the minus 6 years to the minus 1 as the unit. So this would be my rate constant K for something that has a half-life of 2.3 times 10 to the 5th years. All right, number two, how much time needs to go by for 25 milligram sample of CS137 to decay until there is only 8.7 milligrams left? Here's the half-life. So we're going to start with, again, our equation for first order kinetics and go from there. Well, let's see. Oh, well, I'm also going to need, they didn't tell me what my K was, but they did tell me my half-life. So I know my K is equal to 0.693 over T 1/2. So I can plug that into the equation. Instead of negative K, I have negative 0.693 divided by T 1/2 times the time. So let's see what they tell us. I have 25 milligram sample. That is my A0. Until there's only that much left, that's my AT. And they give me my half-life in 30 years. So that's my T 1/2. And they're solving for T. Excellent. So if I do some algebra and rearrange this, I'm going to get my T to equal negative natural log of the amount at some time over the amount that I start with, divided by 0.693 divided by 30.0 years. And then now I can just plug and chug. It's negative natural log of 8.7 milligrams divided by 25 milligrams all over 0.693 divided by 30 years. And when I pick up my calculator and I beep pop boop, I end up with 46 years as my final answer for how long that whole process would take. All right, so yeah, just a little algebra. Number three, the half-life of PO218 is 3.1 minutes. How much remains after 0.4 hours if you started with that many grams? All right, so let's figure this out. So I have a time, right? So this is the half-life. This is my time, but watch the issue here. The half-life they gave me in minutes and the time they gave me is in hours. All right, the grams is my A0, and they want to know, well, what is the amount at some time? Right, so I start with the natural log of AT equals negative. I'm going to skip a step, 0.693 divided by T 1/2 times T plus the natural log of A0. Now they want me to solve for AT. How do I get AT out of the natural log? Well, you got to put the whole other side to the base of E. So it's E to the negative 0.693 divided by T 1/2 times T plus the natural log of A0, and all that is going to be in parentheses as the exponent. And that all equals the amount at some time. So now I can just plug and chug, but this hours I have to convert to minutes. I do 0.40 hours times 60 minutes per hour, that I end up with a time that is in minutes. Which, like, you would think I could just do in my head, but I can't. All right, so I plug and chug e to the negative 0.693 divided by my half-life of 3.1 minutes times my t, which is at 0.4 hours, times 60 minutes per hour, so that my hours cancel out. I'm left with minutes. Minutes cancels out. I'm left with a numberless thing, plus the natural log of the amount that I started with, and it said I started with 155 grams, so 155. And when I plug and chug and I get my final answer, I end up with 0.72 grams. Right, which makes sense because, like, let's say 0.4 hours is like 24 minutes ish, and if each half-life is roughly 3 minutes, we've gone through like 8 half-lives, so we've cut it in half quite a bit. Number 4, lead 210 decays to form mercury 206 and has a half-life of 22.3 years. How many grams of Hg206 would you have after 17.5 years if you started with 7.5 grams of Pb210? All right, so this one is a little tricky. So let's start with the equation. Natural log of At equals negative 0.693 over T1 half times T plus the natural log of A0. So remember, the A0 that we're talking about is for lead 210. So let's keep that straight and you'll see why. So we have a half-life. So we got T1 half, things that were given, T1 half. We got time of 17.5 years, and we have an A0. So let's solve for AT. My AT for lead specifically is negative 0.693 over T1 half of 17.5 years. Oh, I'm sorry, I lied. The half-life is the 22.3 years. I'm sorry, 22.3 years times the 17.5 years plus the natural log of the starting amount, A0, which is 7.5 grams of Pb. So now when I do this, when I plug and chug, oh, I'm sorry, e to the, I forgot. There you go. When you plug and chug and you get all this, you get 4.35 grams of lead remaining. So if we want to know how much mercury was made, we would need to know how much lead is left. So I started with 7.5 grams. I minus the how much is still remaining, and I end up with, what's it, like 3.15 grams of lead decayed. What did it become? Well, it became mercury 206. So lead, if you take a look, has a mass of 210, but it decays into something that has a mass of 206. So I got to do a little mass ratio. So I know for every 210 that I start with, I end up with 206 grams of mercury. So I've converted 3.15 grams of lead to how much mercury. So this, I'm actually gonna have to whip out my calculator because I didn't answer that question. I got the answer for how much is left, but that's not what's being asked. All right, so I do 206 times 3.15 divided by 210. And I end up with 3.09 grams of mercury. All right, there you go. Number 5, cesium-137 has a half-life of 30 years and decays by beta emission. How many beta particles are emitted by 14-gram sample in 3 minutes? All right, so here's an issue. We got 30 years, we got 3 minutes. Those units for time are not the same. But let's start with the equation. Natural log of the amount at some time equals negative 0.693 over T1 half times T plus a natural log at A0. So if I want to know how many beta particles are emitted, I need to know how much decayed. Right, 1 mole decayed gives me 1 mole of beta particles. So let me figure out how much do I have left after that much time. So the amount at some time equals E to the negative 0.693 over T1/2 of 30 years times my time, which is 3 minutes, which I gotta fix because it needs to be something related to years. So I know that there are 60 minutes in 1 hour. I know that there are 24 hours in 1 day. And I know that there are 365 days in 1 year. So my days cancel out, my hours cancel out, my minutes cancel out, and now I'm left with years, which will then cancel out, plus the natural log of A0. Well, I started with 14.0 grams. So when I do all that, I find that the amount I have at that time comes out to be like a 13.9999, a bunch of other digits. It's almost 14 because if the half-life is 30 years, 3 minutes goes by, not a whole lot has decayed. So I'm not going to bother writing all that out, but I am going to use that value as it is in the next step. So if I want to know how much decayed, I got to take a look at how much I started with and subtract it from how much is left. So when I do that, I get the grams remaining, or I'm sorry, grams decayed. And once I get that, I want to divide that by the GFM, the gram formula mass of cesium-137, which is 137 grams per mole. So I take that difference, I divide it by 137 grams per mole, and that is now going to give me the moles decayed. But the problem's asking for individual beta particles. So I got to now times that by Avogadro's number, 6.022 times 10 to the 23rd particles per mole. So now my moles cancel out. And when I do all that math, when I plug and chug, I end up with 8.11 times 10 to the 15th beta particles being emitted in just 3 minutes. Okay, there you go. All right, number 6, last one in the section. How old is a rock that has 0.275 milligrams of lead-206 for each milligram of uranium-238? Half-life for uranium-238 is that. So we have uranium, the mass of 238, which decays in a bunch of steps. I'm not really interested in what those steps are, but it ends with lead-206. So if I start with 238 grams of uranium, I'm going to end up with 206 grams of lead. All right, so that's an important thing to consider, because what they're saying is right now we have a uranium to lead ratio of, for every 1 milligram, we have 0.275 milligrams of lead. So now the question is, well, how much uranium was there to start with? I know some of it decayed, and I ended up with 0.275 milligrams of lead. So how much uranium did that used to be? Well, I'm going to have to use that ratio to figure it out. So I have 0.275 milligrams of lead. How much uranium was that? So I do a little cross multiplying and dividing, and I get X to equal 0.3177 milligrams. So 0.3177 milligrams of uranium decayed to become 0.275 grams of lead. So how much did I start with? Well, there's still 1 milligram left of uranium. So my A0 is really that 1 plus the 0.3177 milligrams, or 1.377 milligrams. So that's my A0. The amount at some time is 1 milligram. They tell me the half-life. So now I can finally go do my first order kinetics equation. Natural log of AT equals that negative 0.693 over T1/2 times T plus the natural log of my starting amount. Now what I'm trying to do is solve for temperature, or not temperature, T, time. So I do a little algebra. I get my time equals the natural log of A0 divided by AT all over 0.693 divided by T1/2. Now I know all of those values, so I can just plug and chug at this point and end up with 1.79 times 10 to the 9th years. All right, so things to watch out for. This lead, the 1 milligram of uranium to 0.275 milligrams of lead. That 0.275 milligrams of lead used to be 0.3177 milligrams of uranium. Right, the mass dropped because uranium decayed, shot off a bunch of particles. So you got to figure out how much uranium to that lead used to be. All right, I hope you found that helpful. See you in class. Goodbye.